Experimental Refutation of Special Relativity by Eugene Stefanovich. Outline. First, I'm going to remind you the well-known fact that the Coulomb field of a fast-moving charge has the form of a flat pancake. Then we will talk about the remarkable Pizzella's experiment, which established that the propagation speed of the Coulomb field exceeds the speed of light, and it's likely to be infinite. I have mentioned this experiment a couple of times in my videos already, but this is such a remarkable achievement that one more reminder wouldn't hurt. Then I'll talk about beam position monitors that are used for qualitative Coulomb field measurements in modern accelerators. Valentino's experiment with a beam collimator at the Large Hadron Collider is another confirmation of the superluminal speed of Coulomb fields. Next, we will see how Maxwell's theory described the Coulomb field of a charge whose trajectory experienced a sudden change. We will note that this situation is realized in accelerators quite often, when charged beams are deflected by dipole magnets. Then I'll analyze a dozen or so modern accelerator designs and show that Maxwell theory cannot explain their successful operation. I will conclude that these observations confirm Wigner-Dirac theory that predicts instantaneous propagation of the Coulomb force. It is a well-known fact that the electric or Coulomb field around a charge at rest forms a spherically symmetric pattern. But if the same charge is moving, then the field lines become compressed. The Coulomb field of a very fast charge forms a thin pancake oriented perpendicular to the direction of velocity. This is a well-known fact, which is true only for charges that were in the state of uniform movement for a very long time. Now suppose that we have a fast charge that emerges suddenly from the surface of a conductor or from a metallic pipe of particle accelerator. In this figure, the charge crosses the conductor surface at point A and moves in the z direction. In Maxwell-Einstein theory, the signal about the charge being released into the open space cannot propagate faster than light. Then the Coulomb field pancake cannot be formed instantaneously. The size of the pancake is limited by the causality sphere that propagates with the speed of light around the point A. From this figure, it's clear that the Coulomb pancake grows gradually in a linear fashion. Its radius is equal to the traveled path, L, divided by the relativistic factor gamma. For relativistic electrons produced by modern accelerators, this factor can reach values of many thousands. This means that the electric field around the electron bunch grows very slowly. If we could register this slow formation of the Coulomb field, this would be an indirect proof of the limited speed of propagation of Coulomb forces. But there is also a different theory of electromagnetic forces. It was described in lecture 7 of my course, Making Sense of QFT. According to this theory, based on Wigner-Dirac ideas, Coulomb fields propagate instantaneously, so the full Coulomb pancake is formed immediately after the charge left the conductor surface. Then the size of the pancake remains unchanged. So, we have two theories predicting different speeds of the Coulomb field. To measure this speed was the idea of an experiment performed in 2012 by the group of Professor Pizzella. They shot bunches of accelerated electrons in the experimental hall. The beam line is shown here by the red arrow. The space around the beam was filled by many electric field sensors with good time resolution. Positions of the sensors are shown by blue stars. The calculation on the right shows that according to the Maxwell-Einstein theory, the radius of the Coulomb field pancake was expected to not exceed 6 millimeters. This means that the pancake was not wider than the red arrow in the figure. And according to classical electrodynamics, the electric field sensors should not register any signal. However, experimental observations were completely different. Quite significant signals were detected, as shown by the green lines. Their forms were the same as if electrons were in a permanent state of uniform movement. In other words, instead of the gradual pancake growth predicted by classical electrodynamics and special relativity, the pancake emerged immediately in the entire space after the electron bunch left the accelerator pipe. This is a strong evidence in favor of the instantaneous propagation of the Coulomb field, and a good reason to question the validity of special relativity. In Pizzella's experiment, the Coulomb field was measured outside the accelerator pipe. But modern accelerators also use so-called beam position monitors for measuring fields inside the pipe. A typical BPM design consists of 4 electrodes inserted in the pipe wall. If the beam goes through the center of the pipe, the voltages on all 4 electrodes are equal. But if the beam is off-center, the voltages are different. From this difference, the software can calculate the shift and send signals to dipole magnets to take the corrective action. Thus, smooth operation of accelerators depend on these beam position monitors. The signals at electrodes are created by the Coulomb pancake field, which is shown on the side view on the right. Therefore, by analyzing accelerator performance, we can draw certain conclusions about the form of this pancake field. Here is one example, an experiment with a beam collimator performed by Gianluca Valentina and his team at the Large Hadron Collider. The beam collimator shown in this figure was intended for beam cleaning. As this figure shows, in the collimator, the charged beam passes through a gap G between two metal blocks. There are beam position monitors installed at the entrances to and at the exit from the collimator. For our discussion, it's important that the electrodes are retracted by 10 mm from the active surface of the jaw. Let us now see what are predictions for the electrode signals by the two electromagnetic theories. In the Maxwell-Einstein theory, the upstream electrodes at the bottom of the figure will measure the full magnitude of the pancake Coulomb field. But we cannot say the same about the downstream electrodes shown in the upper portion of the figure. The theory predicts a slow growth of the pancake field, so the signal at the upstream electrodes is expected to be zero. On the other hand, in Wigner-Dirac theory, the pancake field expands instantaneously, so roughly the same signals are expected at both downstream and upstream electrodes. And this is exactly the result which was found experimentally, as this graph shows. This is another confirmation of the superluminal propagation of Coulomb fields. However, Dr. Valentino and his co-authors did not make this conclusion. So far we discussed charges that moved along straight lines. Some interesting things happen also when charges' direction is changed suddenly by a collision or by action of external force. Before the collision, the charge moved uniformly with its pancake field attached. How the field would look like after the collision? If we believe Einstein's idea of causality, we have to accept the notion of the causality sphere of radius ct. All space points outside this sphere have no idea that the charge was deflected. So the electric field at this point should be exactly the same as if the charge continued its uniform rectilinear motion. These portions of the field are shown by yellow lines. Similarly, the pancake field around the deflected charge cannot emerge instantaneously. Its growth is limited by the same causality sphere. In the literature, these ideas often go by the name of half-dressed or semi-bare particles, which means that after the deflection, the charge keeps only a part of its usual Coulomb field. A completely different behavior is expected from the Wigner-Dirac theory with instantaneous field propagation. In this case, the Coulomb field is permanently attached to the charge and quickly rearranges itself after each collision. Modern accelerators are ideal places for studying the Coulomb field dynamics. In this example, you can see that typical beamlines have multiple dipole magnets that change direction of the accelerated beam and multiple beam position monitors. Dipole magnets are marked by blue circles in this figure, and beam position monitors are marked by red circles. Let us now see in more detail what are expected signals from beam position monitors in the vicinity of dipole magnets. As we discussed above, in Maxwell-Einstein theory, after deflection, the Coulomb field attached to the deflected charge grows in size in proportion to the travel distance L. If the distance between the dipole magnet and the beam position monitor is less than r times gamma, where r is the radius of the pipe and gamma is the relativistic factor, then the BPM cannot measure any signal because the size of the pancake field would be too small. However, there are no restrictions of this sort in the Wigner-Dirac theory, because in this case the size of the Coulomb pancake remains at its maximum at all times. If we now analyze designs of many accelerators available in open sources, we will find many instances when the distance between the dipole magnet and downstream beam position monitor is less than the Maxwell-Einstein theory limit. In the left column of this table, I showed accelerator name. Next is the type of accelerated particle, mostly electrons. Next two columns are particle energy and approximate gamma factor. Distance between the magnet and beam position monitor. And calculated radius of the pancake field in millimeters. In the reported cases, this radius is smaller than the radius of the beam pipe. Then, according to the Maxwell-Einstein theory, this beam position monitor would be silent, and the accelerator would not be able to work, which is of course absurd. The last column is a reference number according to the online publication mentioned at the bottom. Let me now summarize the conclusions. According to Maxwell-Einstein electrodynamics, changes in the Coulomb field cannot propagate faster than the speed of light. However, many experimental measurements do not support this conclusion. Most notably, Pizzella's experiment established the superluminal propagation of the Coulomb field. A similar interpretation can be applied to the Valentino experiment at the Large Hadron Collider. Actually, many modern accelerators would not be able to work in the case of the slow Coulomb field propagation predicted by Maxwell and Einstein. There are many other experiments that support the same conclusions. For the full list, please see my online publication mentioned on the previous slide. Therefore, special relativity has been refuted by experiments. On the other hand, all mentioned observations are in full accord with the Wigner-Dirac version of electrodynamics. Thank you.